So here we are making fun of Manuel because I had forgotten my infinitive auxiliary verb or word there too. Okay, how to tell if a molecular compound will dissolve. Okay, so with this one, there's not going to be some, these nice rules for us to follow. In this case, we just kind of have, some generalizations to make. Since water is polar, the more polar the solute, the more likely it is to dissolve. Yay, we're guessing, yeah. So with this, the idea here is what we call like dissolves like. So if on a multiple choice question you're going to be asked which one of these molecules will dissolve in water, presumably you'll be given one polar molecule and three nonpolar molecules or something like that. And the choice will be to choose the polar one. So because water is very polar, whatever you have that is also polar, it's likely that that will dissolve in the water. So anytime you have something like sugar or ethanol or, let's see, what else do we put in water? That's a molecule. Glucose, I guess that's also sugar. Well, whatever. We have all these molecular compounds as well. Ammonia can dissolve in water. That's another molecular compound, right? So the idea here is like dissolves like. Polar things will dissolve in polar solvents. Non-polar things will dissolve in non-polar solvents. So you can dissolve your vegetable oil in gasoline, or vice versa, but you cannot dissolve your vegetable oil in water. Not going to work. You can also not dissolve your gasoline in water. Because gasoline and vegetable oil are both non-polar. Those two will go together happily, but they will not mix with water. Okay, does that kind of make sense? Kitchen chemistry, we've all kind of seen this before. You'll see that if you were to make a salad dressing, your salt is going to dissolve in the water part, or the vinegar part, since that's going to be the water. And you're going to see that, you're going to get a lot of other flavors, like black pepper or whatever herbs you're putting in will be more likely to go into the vegetable oil part, because those are going to be more non-polar things. So, cool. Okay, so we have one more word to talk about, and I'm going to use it in a sentence. Oil and water are blue immiscible, whereas oil and gasoline are miscible. So, what do we think miscible means? Yeah, it's pretty much exactly, yeah, mixable. I like, yeah. So, it means that two liquids will fully mix/dissolve. Okay, yeah, they're able to mix. And interestingly, when you're dealing with liquids, so you know perhaps that if you keep adding salt to some water, there's going to be a point at which that salt will no longer dissolve. You can keep adding more salt, and you're just going to have salt at the bottom, right? That's called, oh, I guess we haven't talked about that, but that's something you've experienced in real life, perhaps. Or same with sugar. You know, you put enough sugar into your water, it's not going to dissolve anymore. However, with liquid solutes, no matter how much ethanol you put into your water, it will always dissolve. Because miscibility means that these can fully mix together. Yes, it certainly would, Zoe. With salt, you can get a little bit more with heat. However, there is a point at which you would still not be able to dissolve more salt. So at boiling, you know, your salt water is boiling. Hi, Kaz. You would not be able to add more salt. So cool. Alrighty. One other thing to note is, how about purple? All gases are soluble in all other gases. We can also call, it's kind of miscible. So all gases will dissolve in all gases. Anybody have any idea why this will be the case? Why a polar gas will dissolve in a non-polar gas? Like, for example, we have, let's see, we have water vapor, polar, which will dissolve in nitrogen, which is a non-polar gas, right? Anybody have any idea why? The answer lies in intermolecular forces. So oil and water don't mix because the water prefers itself. It can make nice hydrogen bonds with itself that it can't make with oil. And so as a result, those guys will kind of just be separate. However, since gas molecules are so far apart, we assume they don't have any intermolecular forces. And as a result, if you put water vapor into nitrogen gas, they're going to dissolve because they're so far apart they wouldn't be interacting anyway. So there's nothing to say, hey, water molecule, you should be interacting with other water molecules, simply because that water molecule isn't interacting with any molecules. Okay, so that's why all gases are soluble in all gases. So no matter what, you can always mix gases together, because there are no intermolecular forces. Okay, Zoe's got something to say. While she's typing, I'm going to type out or write out our next. They are dissolving, actually, believe it or not, Zoe. Gas solubility is kind of less obvious to us, but air is a solution, right? If Gumbo were to come in here all farting and all that stuff, the smells coming out of his little booty will dissolve in the air. Doesn't matter if those are hydrogen sulfide, which would be a polar molecule, or if it's something like methane, which is nonpolar. Those would still dissolve in the air, and I would smell it, and I'd be like, come on, Gumbo, why are you doing this? So, definitely going to happen. So, they actually don't interact. So we assume gas molecules never interact with each other because they're so far apart. Okay? So it does not matter what type of gas it is, they will always dissolve in each other. Okay? Cool. So, how do we make things dissolve faster, or faster? Let's just say faster. Okay, so Zoe has already got one for us, and she's written it out again. That's awesome. That's one way. Give me two more ways. How do we get something to dissolve faster? Oh, soda is empty. So yeah, we can stir it. And what's our third way? I mean, that would technically work. That's true. Add more water, yeah. Okay, fine, I'll accept that. That's not the one I was going for. But it would work. You're absolutely right. Add more solvent. No one gets it in about... Aha! Yes, perfect. Okay, exactly. Crush it. Yeah. So, yeah, grind it up, whatever. Anything like that. Yeah, so small particles dissolve faster than big ones do. Right? So, if we're thinking about it, all of these kind of have the same rationale behind them. All of these all exist for the same reason. So if we go back to our... Oh, crap. 2 sodiums next to each other. That's not allowed. Okay. Alrighty, so here's our sodium chloride. We have all these water molecules around. Remember, in order for something to dissolve, a bunch of water molecules have to come in and kind of like pluck it off. And so those will now go and form our happy, what's called the hydrated ion. Okay, so the purple is water, right? And the same thing here. Like other water molecules will go ahead and take this one off. Alrighty, eventually, what's going to happen is, I'm just going to do one layer because, forget it, it's going to just take way too long to draw. Eventually, all the water nearby are going to be kind of already hugging these ions. Okay, so this just happens normally. And so, if we look at it, it's going to be a lot harder for, say, this molecule way in the corner to come and grab a chloride, right? It's competing with these other ones. It may say, I'm going to come in here and join with this chloride, or I'm going to go and mess with that sodium. But for this to get all the way over to this chloride, that's hard to do. Okay, after some time, right? When you just put your salt into that water, it's going to dissolve fairly quickly, and then it's going to slow down. Because all this water is already going to be interacting with other ions. Okay, so heating it up. What does heating it up do? What did we define heat as? Exactly right. So the faster all these things are moving, the faster these kind of hydrated ones can get out of the way. And at that point, new water can come in, and that'll be easy for it to grab those ions. All right. By stirring it, we're doing the same thing. We're moving those molecules out of the way so new water can come in to dissolve the salt, or whatever our solute is. All right. In terms of adding more water, yeah, we're just making more free water available. Not necessarily friction, Zoe. It's if you just take some salt and pour it in water and do not touch it and leave it cool, eventually if you do stir it, you're going to see it like that kind of dense like solution at the bottom, that's those ion heavy molecules that if you stir it, you're going to see the ripples through it, for example. Or if you pour like sugar syrup into something, you're going to see those ripples on the bottom. That's just those saturated molecules that are going to be moving out of the way. And so if you can get fresh water down there that does not have an ion on it, it'll be easy to grab. Okay, in crushing it, the same idea. The more surface area we have, the easier it is for water to come in. Because if you have this big-ass crystal, it's going to take a very long time for water to reach those interior ions. So, because water can only get stuff on the surface, so the more surface you have, the faster it will dissolve. Okay? Does that kind of make sense? Somewhat. So, I mean, you've noticed that with sugar, for example, larger crystals take time to dissolve. And also, if you were to try and put large crystals into your iced coffee, just forget it. That's going to take forever. Just because your water molecules are moving slowly by themselves, and even if you're stirring it, they can only hit the ones on the surface. So it's going to take a long time. So, exactly. So if you were to try and put rock candy in it, just forget it's going to take so long to dissolve your sugar into your coffee or whatever. Okay? So, but again, this stuff is kind of like, this from real life. So, cool. But now you know molecularly why this is happening. Alrighty, so we have more definitions here. Since I kind of mentioned one, we have what's called, saturation, which is the point where no more solute will dissolve in the solvent. So trust me, do this. You can do it at home. Take a cup, put some water in it, and just keep adding salt. Okay, keep stirring it, keep doing all that stuff. Eventually, you are going to reach a part where if you keep adding more salt, no matter how much you stir, it is not going to dissolve anymore. And that's what's called saturation. Okay, so a saturated solution has as much solute as it can possibly hold. And so what's happening with all this stuff with like mixing more rapidly, here's our happy water, which of course has ripples for some reason. We have our crystals at the bottom. If we don't stir this, the area just near the bottom will become saturated. So Zoe, very rarely would you exceed 50%. Like, there's no way you can make a 50% salt solution. It just will not happen. You will not be able to dissolve it that much. However, with certain liquids, like Everclear, for example, which is 75% alcohol, actually ethanol is your solvent there, and water will be your solute. So you will kind of flip the roles for certain things. But for solids dissolving in water, not going to happen. The water will always be the solvent. You will not even get close to 50. Okay, so anyways, this area will kind of get saturated. And saturated solutions are always denser because they're holding on to those ions, right? And so what's going to happen is if we don't mix this, we're going to actually form kind of layers in our solution. So you can try this at home too. So just put some salt in some water and just, don't do anything. And if you come back in, 10 minutes or so and just stir it, you're going to see all those ripples at the bottom. And that's going to be this saturated solution mixing with the rest of your solvent. Okay, so that's what's going to happen. Let's see. Perhaps you've seen bartenders can kind of float things on top of each other. That's kind of the same idea as well, as you're forming these kind of layers of saturation that you can mix later, and it'll be exciting. So cool. Okay, so you can have saturated solutions. You can have what are called supersaturated solutions. Where it has more solute than it can handle. Oops, sorry. And so how you get a supersaturated solution by heating it. Heating until saturated. And then slowly cooling. Let me see if there's a good video for you guys on this. Let's see. Let's go to YouTube. Whoops. Okay, this is one that we have in the textbook, but we have it here too. So once this, what am I doing? I can just move this over. Okay, cool. Look, a dog. Yay. Okay, here's a supersaturated solution. So this one has been heated before. Gosh, how long is this video? 10 minutes, forget it. Alright, boring man. We don't need this crap. Yes. Okay, here it is. Okay, I've gone too far. Oh no. Okay. So here's our solution. And he's just going to add a few more crystals. So it's already supersaturated. It can't handle the amount it has now. So it's kind of really unstable. And so just by giving it like one more crystal, it just says, forget it, I'm dead, I can't do this. And it actually will completely crystallize. And so while that was liquid beforehand, it is now solid. And believe it or not, it's actually pretty hot at the bottom too. There's a video of the same exact thing in the textbook, but here's some old man doing it. Yeah, fun. Cool. Okay. Simple syrup, so sugar is interesting in that it will actually dehydrate. It will form caramels. So you can't really supersaturate sugar as easily. But you can do it with salt, I think. Salt will be a little easier. But yes. If you could control it so to prevent it from forming caramels, Zoe, you probably could make supersaturated sugar. But that one with sodium acetate is pretty common. Yeah, exactly. You know what? This is true. So if you've ever made caramel, anyone, if you've got a kind of crappy pan, or your technique is not perfect, you will see crystals forming on the sides of your pan, if you've stirred it or if you've messed with it. So yeah, for sure, you can actually crystallize that, and that's going to ruin your caramel, and it's going to be nasty and gritty and very sad. So yeah, that's definitely a thing that's possible. Yeah, I had to think about that, but definitely true. So that's awesome, Zoe. I didn't know that. So cool. Okie dokie. So let's see. Are we done with vocabulary? No, never. Okay. So we've covered a lot today. We covered solute, or solute-solvent, rather. We talked about ionic compounds dissolving, forming ion-dipole interactions with water. We talked about molecular things dissolving if they're polar, and how polar things will dissolve polar things, non-polar things will dissolve non-polar things. Oh, that's just boring. Sorry. And we also talked about gases dissolving in gases. Alright, we then talked about how to make things dissolve in liquid faster. However, we have one more thing to talk about with solubility, and that is gases dissolving in liquids. Gases don't like this. Well, most gases are non-polar, right? So non-polar gases hate this. They do not want to be dissolved in water because non-polar things don't want to be in water. So, let's just see if you guys can think about this. So, if we want more gas to dissolve in water, and this gas is non-polar, what do you think we might do to it to help it to dissolve? Or force it to? Now think about your real-life example. Okay, I like that. Make it more polar. Unfortunately, it does not work that way, Samuel. You cannot take carbon dioxide and say, okay, now you're going to become polar and you're going to dissolve in my soda. That one will not work. I like your idea of compression condensation. Yeah, okay. That's a good one. That'll work. Let's see if someone can get the other way. Yes, we can cool it. If you yell at it and force it to be polar, it depends how independent the gas is. If it's a sensitive gas, then maybe it'll work. So Zoe, interestingly enough, you totally have the right answer, but liquid nitrogen will freeze the water rather than dissolve in it. So, but you have the right idea. Okay. So we can cool it or add more gas. Okay, so cooling it. So let's see, where was our water molecule? Here are our happy water molecules. Nice and polar. Uh-oh, here has come a carbon dioxide. Alrighty, so if we want this carbon dioxide to come into this water, if we cool it down, that gives the water less time, basically, to get away from the carbon dioxide. So the slower that water is moving, the longer it's going to take to move away from the carbon dioxide. So if you want to make your carbon dioxide dissolve in... That's pretty funny, Jaws. Yeah, it's the evil water molecules. So the slower these water molecules are moving, the more kind of tolerant they are of the carbon dioxide. Maybe they're not even noticing it's there. They're slow, they're lethargic, they're kind of like, oh, there's carbon dioxide, oh, whatever, it's okay. I don't like it, but whatever. However, if they're, moving quickly, oh, forget it, I don't want to see that carbon dioxide, I hate it, I don't want to blah, 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 blah. So, real-life example. If we were to take this soda can and put it outside on one of these lovely 90-degree days, and after a few hours we came and opened it, what would happen? Yeah, it's being forced into a loveless relationship. What would happen if I had a hot soda and opened it up? Yeah, no one wants to be there. It would explode, right? And then it would be flat. So as soon as I opened the container, it would just... Because all of that gas, the water is like, forget it, you can't be here anymore. And as soon as I'm allowing that pressure to release by opening the can or the bottle, it is going to just explode, basically. And then it will be flat after that, Marissa. You're absolutely right. So it's just going to kind of dissolve or get out as soon as it can. However, if we have it nice and cold, we're going to be able to open it normally, and it's not going to explode everywhere. However, the gas will still be escaping just because we have so much of it dissolved in there. Okay, and so in the factory where they're putting the carbon dioxide into these, the way you can force it to kind of get in there is you add more gas. So if you have a lot of carbon dioxide right on top of that water, just the pressure of it will force it to go in the water. So formally, this is called increasing the pressure of your gas, in this case CO2, which is orange for some reason. And this is something called Henry's Law. You do not need to know that name, but you might see that in your life at some point. Henry's Law is telling us that the larger the partial pressure of gas above our solution, the more gas will go into the solution. Alrighty. So much. We have one more bit of terminology today, after which we will adjourn. And then on Wednesday, we'll talk about a few things calculation-wise relating to these solutions. And then we'll just start talking about chemical reactions. Okay. So the last thing we have are called electrolytes. Okay, let's see what Zoe has. No, I have not given you homework yet, I hope. So you're going to have homework 8 and 9, which will presumably be due, I don't know. We'll find out. We'll figure it out, Zoe. There's nothing due, soon. Okay, electrolytes. So, you've heard about this in Gatorade, right? That's going to be dissolved things that conduct electricity. Alrighty, we can get this from the word electrolyte itself. Light, for all you biologists, lysis is breaking something, right? So if you break this molecule up, does it conduct electricity in solution? That's what an electrolyte is asking. We're going to see we have several flavors. We have strong electrolytes. We have weak electrolytes. And we're going to have non-electrolytes. So there is a video in the textbook for us about experimentally how we'll determine this, but since we are zooming, we are going to just talk about them. So that is going to be ionic, soluble compounds. You know what? That doesn't work for me. Soluble ionic compounds. Is in English a weird language? Like adjectives have to come in a particular order or else we get upset. Yeah, English is weird. Other languages you can just throw these adjectives around, nobody cares, everyone will understand. Anyways, and then we also have what are called strong acids. Okay, weak electrolytes are going to be weak acids. And non-electrolytes will be polar molecular compounds. Alright, strong ones, that means they dissolve and dissociate, that means separate completely. So if we write out, let's do green, this really means that we have actually sodium ions and chloride ions that are dissolved. So sodium chloride, because it is a soluble ionic compound, will split apart completely in solution. Okay, so it is good. And then if you were to try and conduct electricity with this, you would see it would conduct very nicely. So electricity is conducted when you have charged things in your liquid. So if you have the choice of, during your thunderstorm, to play in a freshwater lake or the ocean, neither of which is a good idea, please don't, playing around in the ocean during a lightning storm would be far worse for you than playing around in a freshwater pool or lake or something, because the salt that's dissolved in the ocean will help it conduct electricity. So if you get zapped, or the ocean gets zapped, it's going to conduct that electricity very quickly and very efficiently right onto you, and it'll kill you. In the pool, water will still conduct some electricity, but not nearly as much as salt water. Okay? Fun. This is also why in our bodies we have sodium chloride within our blood, right? That's the plasma is mostly sodium chloride solution. And then inside, so Zoe, that's an interesting question. It would be slightly worse for you if you were hot and sweaty, yes. Yes. What was I saying? Now look at you've distracted me. Yeah, should be. Guys, what were we saying? Okay, anyways. So strong electrolytes will dissociate completely. Oh, yeah. So the pool will not conduct electricity as nicely. Okay, cool. So, yeah, go ahead and watch the video in the textbook. It'll be pretty cool, so you can see directly how that's happening. Okay. Weak electrolyte. So, for example, a weak electrolyte, what color are we using for that? Blue. Dissociate a little bit. For example, acetic acid is actually, I'm going to use a special type of arrow here. Okay, so, biology time. So, our bodies, our blood plasma is made of sodium chloride. About 137 millimolar of sodium chloride, right? When we sweat, our interstitial fluid, the fluid in between our cells, is also sodium chloride based. And so when we sweat, that sodium chloride goes outside of our body. And so if you were to ever, taste sweat, like if you were to lick yourself after being at the gym, you're going to taste it tastes salty. So if you were to just go after exercising and drink pure water, that would not be a good idea, because when that water goes into your body, it's going to dilute the sodium chloride. So you've lost salt, basically. You've pushed salt out of your body. And if you're just putting water back in, you're not putting salt back in. And so as a result, there's going to be a kind of imbalance happening here. So if you consume water that has a little bit of salt in it, like Gatorade does, or really most things do have some salt content, like you can see the soda, which has been the star of today's show. You'll see it has 40 milligrams of sodium, so it does contain some electrolyte content. And so when you're drinking things that have that, they're going to help replenish the salt that you've put out through your sweat. So that's kind of how it makes you more hydrated, just maintaining the balance. Yeah, exactly. So, you definitely don't want to be drinking distilled water when you're sweating a lot. Okay? Conversely, you don't want to be drinking salt water either, because that's too much salt. So you're putting more salt in your body than it can handle. That's going to actually pull water out of your cells and shrivel them up, and they'll die. So not a good thing either. Balance. That's what biology is all about. Anyways, back to weak electrolytes. Those are going to be what are called weak acids. We'll talk about strong acids, weak acids. Weak acids will dissociate a little bit. So what this means is that for every 1,000 acetic acids that you put into your water, about one of them will break into H plus and acetate ions. The rest are going to stick together as acetic acid. And so we're going to see that because this only dissociates a little bit, it's not going to conduct electricity as well. It'll still be better than pure water, but it will not nearly be good as a strong electrolyte. All right, and non-electrolytes, what color did we do for that? Purple. Okay. They don't dissociate. So they will dissolve, but they will not dissociate. That means they don't break apart. So for example, if we put some glucose into water, it stays as glucose. It does not change. There's no ions here. Okay, and those are going to be your polar molecular compounds, right? Non-polar ones won't dissolve in water. Polar ones will dissolve, but they will not break apart. Ionic compounds that dissolve will fully break apart. And weak acids are going to be a special case that are going to only break apart a little bit. Okay, so back to strong. So remember that strong electrolytes break apart completely. This will be important for when we talk about chemical reactions. Okay, so remember this is all soluble ionic compounds and all strong acids. Those strong acids are going to be these three, and last but not least, these 6 acids, which you will want to know, will also fully break up. So if you put HCl into water, all of that HCl will break into H plus and Cl minus. Okay, all of it. All 6 of these, okay, are what are called strong acids. They will completely break apart. All other acids are weak acids. All otter acids. So that's going to be, for example, acetic acid, or oxalic acid, or why can't I think of any? Hydrofluoric acid, or whatever, phosphoric acid. Those are going to all be weak acids, okay? Etc. So these 6 are the strong acids, fully dissolving, fully dissociating. The other acids will dissolve, but they will only break apart a little bit. Okay, most of it is going to stay together, and a few of them will break apart. Okay, this is a dynamic process, by the way. Like, the ones that break apart will come back together, and other ones will break apart later, and so it's just kind of always happening. Okay. We'll talk about Van Hoff factor next time. Okay, story time. Not story time. News time, I guess. So, you should have gotten an email today, maybe, that fall semester will also be online. Okay, so summer is definitely online, and now they have just informed us that fall will also be online. So just so you know, that's going to be what's going to happen in the fall. So obviously I have no control of that. And a number of you have asked about my makeup ritual. No, have asked about me teaching 101. Yeah, you're still enrolled, Zoe. You typically only need to do spring and fall to maintain enrollment. But in terms of what I'll be teaching next semester, I have no idea. Um, I do believe it is a firm decision, Marissa. I believe it is going to be online, and there's no changing that. As far as I know. That's the way it sounded. We got the same email that you guys did, so I'm assuming it's firm. I don't know what I'll be teaching. I may not be at GCC next semester anyway, so I had some really awesome interviews last week, so we'll see. I may be around, I may not. I will let you guys know, but we'll see. However, if it is online, I can teach from wherever I am, so maybe we'll be able to see each other in the future. So just letting you know all that stuff. So summer, fall, online. And yeah, I can't change that. So, cool. Okay. Hopefully, your lab stuff should be coming to a close as well. You should have, I think your solutions experiment is tomorrow, and then, did you guys do solutions already? I don't remember. You have not done so. Okay, so solutions will probably be, tomorrow, and then the week after will be titration, which will be a chemical reaction involving molarity and stuff. So, yeah, it'll be exciting. Actually, no, that might be, I don't know what you guys are doing, so forget it. I'm sure Gellert will let you know.